Okay. Any questions about the reactions? We're going to try and sum up some of those today, but any questions to start with? All right, so if we look at if I look today was going to be formation of epoxides, hydrogenation, and then we've got oxidation states of carbon were the three topics for today. So in terms of the reactions, those reactions, let's talk about forming epoxides because it kind of fits into what we talked about on Monday. Wait, what's going on? Okay. So what we did on Monday was the final reaction was to add bromine and water to an alkene. Okay. And so again, for every one of these, we need to know what are we adding and how are we adding it, and then how are we adding it. So what am I adding with a Br2 and an H2O? What two things am I adding? A Br and an OH, Markovnikov or anti-Markovnikov? Markovnikov meaning who is the electrophile? Br plus is the electrophile. And which carbon is it going to add to? The carbon with the most hydrogens. Okay. We only have a few more reactions left, but you're going to have to kind of know those. You're going to have to get them down because all these reactions are going to be on the next test, both from a mechanisms point or writing the products. And if you know what you're adding and how you're adding it and how you're adding it, then you'll be able to get the products really quickly. And we'll also need that for stereo and regioselectivity as well. But we'll talk about this. So I'm going to add Markovnikov, which means that the Br plus, in essence, is what's going to add to the carbon with the most hydrogens. 100% cis, 100% trans, 50-50 for Br and OH. Trans because it goes through the triangle. Now, in this case, it doesn't quite matter whether it's cis or trans because it's not a cyclic system. Okay. So I'm going to end up adding the OH to the CH and adding the Br to the CH2. And this is what we call a bromohydrin. Now, bromohydrins have basically one use, and that is they can be used to make epoxides. And an epoxide is a three-membered ring with an oxygen in one of the positions. So the first way we can make an epoxide is to say, I'm going to react this bromohydrin with something like hydroxide or a stronger base. And you might think, well, the hydroxide could come in and do an SN2 reaction on the bromine. It actually won't. What the hydroxide will do is it will come in and it will kind of deprotonate that OH. Later on, we'll modify this to say it just deprotonates a tiny bit of the OH, but it deprotonates the OH nonetheless. So then what happens is now I have an O minus where that hydroxide was. where the OH group was. So now this molecule, because the bromine and the OH group added trans, is now perfectly set up to do an intramolecular, meaning within the same molecule, SN2. Because the O- is going to attack the backside of the CH2 and kick off the bromine. And again, this is perfectly set up because I added the Br and the OH 100% trans. So when it kicks off the bromine, what I end up doing is I now end up forming the oxygen bonds between the CH and the CH2. And so this is what is called an epoxide. An epoxide is a common name. This is actually called an oxirane, is the IUPAC name. But an epoxide has the three-membered ring with an oxygen in it. So bromohydrin, when you make a bromohydrin, you can simply deprotonate it and then have it do an SN2, reaction, an internal one, to make the epoxide. And so that's method number one to make an epoxide. And all this stuff kind of fits together, so that picks up from where we left off on Monday in terms of why would you even worry about a bromohydrin? Because I can do this with it. Okay. So that's the one thing we can do with a bromohydrin. Okay, so I make this epoxide. There is a much more direct method to make an epoxide, and that is to take that same double bond and react with it what's called a peroxy acid. So a carboxylic acid is a C double bond O OH. When you add an extra oxygen to things, it's always a per. Example, HOH is water. I suppose you could call it hydrogen oxide or hydrogen dihydrogen monoxide, which you'll sometimes read in spoof safety data sheets, because they have safety data sheets for dihydrogen monoxide, and people are like, oh, keep that stuff away from me, it'll kill you, right? Because water will kill you if you're immersed in it, right? So they create those websites, and then everybody wants to be no dihydrogen monoxide, and then it's like, but it's water. Take dihydrogen monoxide and add another oxygen to it, and it's hydrogen peroxide. Right? So this is a peroxy acid. Peroxy acids, what they do is that extra oxygen in the peroxy acid is basically going to plop down on top of the double bond to make the epoxide in one shot. So this isn't really the mechanism, but if you want to think of it this way, what happens is the oxygen, one of the oxygens off of the peroxy acid, basically we could kind of think of it as this pair of electrons moves up here, this pair of electrons moves down there, and then the hydrogen kind of moves there. But what I'm doing is I'm putting the oxygen directly on top of the double bond so that I'm making the epoxide in one step. So there's no add the oxygen to one carbon, maybe the other carbon spins around. It's that oxygen gets added to the top or the bottom, and it forms the epoxide. And what this means is, in terms of the stereochemistry, is that if I had, for instance, if I said I have this trans alkene, and this isn't the same one that I just did, but if I have this trans alkene, when I react it with the peroxy acid, I end up with the stereochemistry being preserved so that if the ethyl group and the methyl group were trans, then the ethyl group and the methyl group will end up trans in the epoxide. Because the oxygen just plops right down on the double bond, whatever the stereochemistry was to begin with, it has to be that way at the end. So trans forms trans. And we'll have to define what that reaction is, because we need to talk about stereoselective, we need to talk about regioselective, and there is a third term called stereospecific, which is what this reaction is. But I want to make sure we're all on the same page with stereoselective and stereospecific. It would seem as if it means something else, but it doesn't. So this reaction is what I'm going to call stereospecific. Okay. So trans will form a trans epoxide, cis alkene will form a cis epoxide, because it's a one-step mechanism. So the preferred method to make epoxides is to react peroxy acids with double bonds. So that's how we make the epoxides. All right. Really, other than the mechanism for forming the bromohydrin, deprotonating it and putting it into an epoxide, the peroxy acid is just one step. All right, so is everybody okay with that? So I'm just going to make this epoxide. Then the question is, what do I do with the epoxide? Which this all flows together. So first of all, an epoxide is a triangle. So now's the time to talk about the epoxide being a triangle after we talked about the triangular intermediates that we had on Monday. Well, what can you do with an epoxide? What you can do with an epoxide is you can open it up. It's called epoxide ring opening. And there's two ways to do this. We're just going to talk about how do I do this with acid. So let's say I wanted to add HBr to this epoxide. Actually, you know what? I'm going to change that. Let's add H plus and CH3OH to this epoxide. So it'll be more similar to what we did on Wednesday. No, today's Wednesday, Monday. So if I'm going to react this epoxide with H plus, what's my first step in the mechanism? I'm going to protonate the oxygen, right? Anytime you have an oxygen-containing species and you add acid to it, the first step you do is protonate the oxygen. Okay? So I'm going to protonate that oxygen. And that's going to form an oxonium ion. Is that oxygen happy with that positive charge? It can tolerate it, but is it happy? No, it would be better off if some other element could take on that positive charge. So what's that oxygen plus going to do? It's going to push its charge down to those two carbons. So we can think of this epoxide once it's protonated like this. Why did I write it like that? Right? We should be having a sense of déjà vu, which means we've seen this before in French. Where did we see this before? I'll give you two choices. You have two choices to give me. Where did I see a structure like that before?
Was it mercury bridging?
The mercury bridged. The mercury formed the triangle, so we saw it in on mercuration, demercuration. What also bridged into a triangle? Okay, one. The bromine and the bromonium ion. So we can think of this protonated epoxide as being exactly like those two triangular intermediates. Because in essence, that's what it's doing. Once I protonate the oxygen, it's going to push all of its electron density to the carbon. So I have carbon A and carbon B. I have a methanol molecule. You are the methanol molecule. Are you a strong or weak nucleophile? All right, on three. Strong or weak? 1, 2. You're weak. Which carbon are you going to attack? Carbon A or B? On 3. Which one are you attacking, A or B? 1, 2. Do we need to vote? Let's vote. Which carbon are you going to attack as the methanol, A or B? Okay. Well, first of all, there's only 22 people here. I know how to solve that in the future. After next week, when everybody's back from their full Thanksgiving vacation. Don't ask me if we're having class on Tuesday or not. Right, I've already been through that once. That rant once. We are. If the university didn't want us to have a class on Tuesday, they would have started vacation earlier. Right. So, all right, we got a 15-7 vote. Discuss for a moment as to which one it is. Yeah.
When you say like which one attacks the methanol, you mean which one the OH is going to bond to, right?
No, I mean which one is the methanol going to bond to?
Okay.
So the methanol is going to come in, and it's going to attack one of those two carbons. The OH will slide over to the other carbon, but what my intent is, which one is the methanol going to end up bonded to, A or B? Even if you misinterpreted the question, it's still close enough where we need to discuss. So discuss, and then we'll revote. So which one is the methanol going to attack? We ready to revote? All right, which one is the methanol going to end up on to? Carbon A or carbon B? (17 to 5). A. So your vote is for A. Why?
OH is going to swing over to carbon B, and carbon A is going to become the carbon cation because it's more stable because of the secondary carbon cation, whereas B would only form that primary carbon cation, which is not stable.
I like most of that answer. The part that I don't like is the swinging before the attack.
It'll swing to B when methanol attacks.
Exactly. If it swings over to either one of these, that's going to leave a pure carbocation. And what we know from what we know from this reaction, which I guess I didn't tell you, is that the methanol and the OH are going to end up 100% trans. But whenever you have a triangular intermediate, it will always be 100% trans. So if it swung over, then we'd get a 50-50 mix. So this triangle still has to stay intact. The methanol is going to add to the carbon with the most delta positive charge. And which carbon is that? It's A, because it looks like, in this case, it looks like a secondary carbocation, whereas carbon B looks more like a primary carbocation, which is not stable. So it's just like I went through on Monday. You're a weak nucleophile. You have to give to the carbon that's the poorest. Which carbon is the poorest? It's going to be A, because it has the greatest positive charge, because it has one alkyl group that can help stabilize that so it can take on more of the charge. And so therefore the methanol will add to carbon A. And it will add 100% trans. So in terms of our product, we're going to have the O, the CH3 with the H with the plus charge. Then we're going to have the CH2 with now the OH up there. And so what happens? We lose the H plus from the methanol, and that makes the H plus the catalyst for the reaction, and the OCH3 and the OH now added 100% trans in the reaction. Now, one thing I should say here is this reaction is not, there's no Markovnikov or anti-Markovnikov to this reaction, because I'm adding a nucleophile, an acid, to an epoxide. The only time we have Markovnikov or anti-Markovnikov addition is if we have a carbon-carbon double bond. So this allows me to add the OR group of the alcohol with the OH group. And so I can end up with that sort of hydroxy ether. Now the reason I showed you methanol here is because we can go back now to Monday's bromohydrin, and if I changed it from bromine to adding bromine and methanol, you would end up with the OCH3 added to the double bond. Or if I took mercury and I added alcohol instead of water, I would end up with the ether. So all those reactions that have water in them can also have alcohols, and they'll go by pretty much the same mechanism. So anytime we open up an epoxide, and that's what we're doing, we're opening it up. Anytime we open it up under acidic conditions, okay, so whenever we do acidic epoxide ring opening, then we're always going to end up adding the nucleophile to the most substituted carbon of this carbon-carbon double bond. That's the rule. So when we do acidic ring opening, or what's sometimes called acid catalyzed ring opening, you're always going to end up with the nucleophile adding to the most substituted carbon. And the reason for that is because once I protonate the oxygen, that feeds the positive charge down to the two carbons, and so the carbon with the most positive charge is going to be the one that the nucleophile adds to, and by definition that has to be the most substitute.
Can you repeat why it's not considered
Markovnikov and anti-Markovnikov only refer to adding something to a double bond. Once we convert that double bond to an epoxide, Markovnikov and anti-Markovnikov don't apply. Although there will be, you can do things with epoxides that you can also do with adding directly to the double bond. And we'll talk about that once we've got all the reactions down and we've got problems. Okay, so we make the epoxide, we open it up with acid. The acid protonates the oxygen, then the other group comes in and adds to the most substitute carbon, 100% trans. Okay. All right. Does that make sense to everybody? And I can do this reaction with a number of different groups, but right now only acidic. So I could react this with H plus H2O. I could react this with H plus alcohol. I could react this with H plus and Br minus, or maybe Cl minus. So any of these ring openings are going to have the nucleophile adding to the most substituted carbon, but it's always going to be 100% trans. Right. Let me just show you. Okay, so if I took this methyl cyclohexene, Bless you. And I added Br2 and H2O to that. What would my final product look like? So my first question would be, Br2, H2O, what am I adding? Seems like I just asked this question about 20 minutes ago. Br and OH. Okay, where is the Br going to add? To the top carbon or the bottom carbon? Which one? Bottom one? Because the Br is the electrophile, and so it's going to add to the carbon with the most hydrogens, which in this case is the bottom carbon. So I'm going to add my Br there, and I'm going to add my OH up here. Okay, the reason I'm not putting bonds is because now I'm going to do the stereochemistry. So for the stereochemistry, how did the Br and OH add? Triangle, 100% trans. So as long as the bromine and the OH group get opposite wedges, that's trans. So this would be my major product of that reaction. And because it came from the double bond, I would say it's Markovnikov addition, because the Br is playing the role of the H+. But what if I wanted to make the opposite product? What if I wanted the bromine to be attached to the top and the OH attached to the bottom? How would I do that? Well, let's say I use a peroxy acid here, and I make the epoxide. So when I make the epoxide, I'm going to have, and those are wedges, not dotted lines. If you want, you can put bold wedges in there. It just shows that the epoxide added to one side or the other. If I now add H plus and Br minus, in other words, HBr, if I add HBr to this double bond, what am I going to do? Well, first thing I'm going to do is I'm going to protonate the epoxide. So now I'm going to end up with basically delta positive charges there. And then where is my Br minus going to add? So I protonate my epoxide. Where is my Br minus going to add? To the carbon with the most delta positive, the carbon with the most substitution, the most substituted, which is top or bottom. Which carbon's that going to be? The most substituted carbon, is it at the top or is it the bottom? Top. So the Br minus is going to come in. It's going to add to that carbon. Then your OH swings over. And what did I just make? The bromine and the OH have to have opposite wedges, opposite stereochemistry. What did I just make? I made the opposite product of what I got from from forming the bromohydrin directly. Okay. So what an epoxide can do is, for instance, it can give you the ability to form the opposite product of a bromohydrin by going through the epoxide, particularly with HBr. So I can make either one of these products, and what happens is that makes organic chemistry more powerful, because there's always the yin and the yang of organic chemistry. There's always the Zaitsev-Hoffman. In this case, there's Markovnikov, anti-Markovnikov. So there's usually a set of reagents that do one thing, and there's another set of reagents that do exactly the opposite. If there wasn't, you wouldn't be able to do as many organic reactions as you can, and the organic reactions we have now let us, make our modern day pharmaceuticals and plastics and everything else that we need. So organic would not have developed without the ability to do both. And so this is an example of, okay, one step gives me the bromine on the carbon with the most hydrogens, 2 steps, opposite. All right, everybody still kind of with me? So this is how epoxides can be used. If I added H plus H2O, I would end up with 2 OHs. If I added H plus an ROH, we've already seen you end up with an OH and an OR. And then if you add HBr, HCl, you end up with the OH and the bromine or the chlorine. All right, so that's the epoxides. And we'll come back to epoxides probably next semester when we talk about alcohols. And we'll talk about what happens when you don't use acid. But usually we talk about acid first. Sometimes I'll talk about acid and base, but I'm not going to do that. To confuse things, I'm just going to leave it as acid for the moment. Okay. The other reaction for today was hydrogenation. It's a pretty straightforward one. So, hydrogenation, if I take a double bond and I want to reduce this molecule. Now, talked a little bit about this in lab. Reduction and oxidation are both rooted in the same principle, which is for reduction, it's gain of electrons. And for oxidation, it's you lose electrons. Which I use the Leo the Lion goes grr, saying there's an oil rig. Again, I don't know, I forget what oil rig stands for, but I like the Leo the Lion a little bit better. In organic, the problem is that it's really difficult to keep track of oxidation numbers. It's not difficult, it's just tedious. It's not like metals. Oh, the metal went from +3 to +2. Easy enough to figure out. And that's what the middle part of this is, determining oxidation states of carbon. But we can define in organic the reduction as either the loss of oxygen or the gain of hydrogen. And oxidation would be gain of oxygen or loss of hydrogen. So we can define those two terms simply by whether a molecule gains oxygen or loses it. Whether it gains hydrogen or loses it. So that's a little bit easier method. And in our yeast experiment, we turned a carbon-oxygen double bond into a CH-OH bond. So that molecule gained hydrogens. and under wet reduction. Okay. Now, we can reduce a double bond to a single bond. And what I'm going to do is I'm going to use hydrogen. So that would make the most sense, because if I add hydrogen, I'm going to add 2 H's to the double bond. But this requires either a palladium or a platinum catalyst. Okay. And what will happen is I will add 2 H's. Since I'm adding 2 of the same thing, there is no Markovnikov anti-Markovnikov. And what I find is that those 2 hydrogens added 100% cis. There's no trans. They added 100% cis. So if we're making a table, which we'll do here, if not Friday, we'll do it on Monday after we've done all the reactions. But you can start ahead of time if you'd like. If I'm making a table of all these reactions of what am I adding, Markovnikov, anti-Markovnikov, and then stereochemistry, this one would be 2 H's, neither Markovnikov, anti-Markovnikov, 100% cis. And so I know in this case that my reaction is going to be add the 2 hydrogens 100% cis. The mechanism for this reaction is probably not fully understood at the truly molecular level. There's probably a good idea of how it works, but the problem is that when we have our platinum or our palladium metal, it's a surface reaction. So what happens is that the hydrogen comes down and bonds to the surface of the palladium or platinum. And so then the double bond comes in, and the double bond comes in and adds, so that basically you could think about it adding sort of like this, pair of electrons to the hydrogen, pair of electrons that way. So to put it in the context of what we've talked about before, your platinum palladium catalyst is going to basically go through, or is going to be the table on which sits your hydrogens and your double bond, so that basically what you have is you have a square transition state, give or take. And so what we said before was the square transition state always gives cis. Now you'd have to go back and remember, where did I see the square transition state before? You saw it in the hydroboration oxidation. When the boron and the hydrogen added, they added as a square 100% cis. The real details on this of what happens at the surface is what's probably well known, but not completely, because it's a heterogeneous system. So these kinds of systems are what are used to take a double bond and make an alkane out of it. Okay. The most relevant of these reactions to you would be, there are long-chained fatty acids, long-chain carboxylic acids called fatty acids. And so those long-chained fatty acids can either be fats or they can be oils. The real technical definition is a fat is a solid, an oil is a liquid. That's how we define the difference between a fat and an oil. So you have lots of these that can occur. And usually what happens is that the carboxylic acid might be tied up as a triglyceride ester that you might talk about in biology, like triglycerides are considered fats. And a triglyceride would have not the fatty acid, but it would have, as its ester part, it would have glycerol, and then attached to each one of those would be my fatty acid. Okay. So that's technically this is technically a triglyceride. And so that is either a fat if it's a solid or an oil if it's a liquid. So if we're going to the grocery store and we're buying triglycerides, we have lots of choices. We have coconut oil that's a solid. It's a low melting solid, but it's a solid nonetheless. We can go via vegetable or canola oil, which would be a liquid. And the real difference in those fats and oils is the length of the chain, but also whether they have a double bond or not. So if they don't have a double bond, they are called saturated, because maximum hydrogen per carbon. If, on the other hand, somewhere down the line they have a double bond, they are called unsaturated. And that double bond can be either cis or trans. It turns out that the saturated tend to be solids. They tend to be fats. The unsaturated, because of the kink in the double bond, doesn't let them pack very well. And so unsaturated tend to be oils. Well, number of things you can do with fats and oils. You can make soaps out of them that we'll talk about next semester. Or you can actually convert a liquid oil into a solid fat. So if you go and you buy your Crisco, well, why did you make that face about Crisco? It's not noted to be healthy. Why is it not noted to be healthy? Number one, because it's a solid saturated fats, and I think those are bad, right? But how do you convert an unsaturated to a saturated? What you do is you add hydrogen with palladium and platinum to it, and you solidify your oil into a fat. So your Criscos and your non-natural fats are hydrogenated, which then leads you to the fact that if you don't completely hydrogenate your fat or completely hydrogenate your oil, you end up with a partially hydrogenated fat. And those are bad. And then you can end up with trans fats versus, I don't think they're cis fats, but usually it's the trans fats, right, that everybody's either saying are good or bad. And this cycles back and forth. Coconut oil is good. Coconut oils kill you. I mean, it all goes back and forth in the nutrition. But this is where you see that result of hydrogenation. So if you're gonna make your Christmas cookies out of Crisco, which is common for most recipes because they go back to when Crisco was called oleo, you're going to be using a hydrogenated oil. So that hydrogenation is what's important. Okay. So if you want your assignments, you can come get them. Otherwise, I guess I'll give them out on Friday, or lab if you're in my lab. For Friday, we're going to talk about our last couple reactions, and then we'll either talk about regiostereoselective, or we'll hold that off until Monday, and we'll use Monday and Tuesday next week to go over that and review double bonds. Okay?